Welcome back to the deep dive. Today we're tackling a topic that honestly on the surface feels a bit like the nutritional equivalent of eating dry toast.
Yeah, it definitely has a reputation for being a little, arid.
Arid is a very polite way to put it. We are talking about database normalization, and I think for a lot of people that phrase just conjures up images of dusty textbooks, flickering fluorescent lights, and late night cramming for some computer science exam.
Totally.
But looking at the research we've pulled together for this deep dive, this isn't really just about computers, is it? It feels a lot more like...
Structural engineering.
Yes, exactly.
That is the perfect analogy. Think of it this way. If you build a skyscraper on a swamp, it sinks.
Right.
It doesn't matter how beautiful the glass is on the outside or how fast the elevators are. If the foundation is just slush, the building comes down.
Right.
Database normalization is that foundation. It's the art of organizing information so that it doesn't eventually, collapse under its own weight.
When we say collapse, we really aren't being dramatic here. We're talking about data literally disappearing, becoming contradictory, or just bloating up until the whole system crawls to a halt.
Exactly. The mission here is precision. We take a messy, chaotic table of data, which honestly is usually how data starts out, when humans just throw things into a spreadsheet and we apply a set of strict rules to it.
And these rules are the normal forms.
Right. The goal is to reach a state where every piece of data lives in exactly one place. No duplicates, no ambiguity, just totally clean logic.
Okay. Before we get into the how, and I know we have a whole alphabet soup of acronyms coming our way, like 1NF, 2NF, BCNF, I want to stick with the why for a second, because if you're listening to this and you just have a spreadsheet with all your customers in it and it looks fine to you.
Why bother?
Right. Why go through the trouble of slicing it up into a dozen different tables?
You bother because of anomalies. In the database world, an anomaly isn't just a quirk or a weird little glitch. It is a structural failure. It basically means your database is effectively lying to you.
Wow.
Yeah, we usually track 3 specific nightmares: insert, update, and delete anomalies.
Let's walk through those, because I think actually feeling the pain of these anomalies makes the whole solution make a lot more sense. Let's start with the insert anomaly.
Okay, imagine a simple flat table. You store everything about a university in one big sheet. You've got columns for student name, course name, professor, and so on. An insert anomaly is when you literally cannot record a fact because the table structure itself fights you.
Give me a concrete example of that.
Sure. Say you hire a new professor. They're brilliant, they're on the payroll, they have an office, but the semester hasn't started yet, so they haven't been assigned a specific class to teach.
Makes sense.
If your table is built so that every single row must include a course ID, because maybe that's part of how you organize the rows, you cannot add that professor to the system.
Because the course column can't be empty.
Exactly. So you're stuck. You either don't add them, which means your HR data is incomplete and they don't get paid, or you have to invent a fake course, called TBD or dummy course, just to satisfy the database rules. You are literally forced to insert garbage data just to store a simple truth.
That's incredibly frustrating. It's like trying to save a contact on your phone, but it won't let you unless you also put in their birthday, and you don't know it. So you just lie and say January 1st.
It's a perfect comparison. And now your data is dirty because you've got a fake birthday floating around in there. That's an insert anomaly.
Okay.
Next is the update anomaly, which is probably the most common one. This is the nightmare of redundancy.
This is where we have the exact same information written down in 20 different places.
Right. Let's say you have a student, let's call him John. John is super ambitious. He's taking 10 different classes. In a flat, unnormalized table, you list John's name, his phone number, and his home address on every single row for every class he takes.
So John appears 10 times. John Math, John Science, John History.
Exactly. Now imagine John moves to a new apartment. You have to update his address. But you don't update it once. You have to find all 10 rows. If you update 9 of them but miss the 10th one because you were scrolling too fast,
then John lives in 2 places at once. He's Schrodinger's student.
Precisely. Your data is now inconsistent. If you query the database for John's address, which one does it give you, the old one or the new one? You can't trust your own system anymore. That is an update anomaly.
And finally, the most dangerous one, the delete anomaly. This is the one that sounded genuinely scary in the source notes. Accidentally wiping out history.
It happens all the time in bad designs. Go back to our table where student info and course info are all mixed together. Suppose John decides to drop his physics class. It was a mistake. He hates physics. And let's say that was the only class he was currently registered for.
Okay, so I just delete the row that says John Physics.
But because John's phone number, his ID, and his address were only stored on that specific row when you delete the class, you delete John.
Wow. So he's just gone. Not just unenrolled, but completely erased from the university records.
Exactly. You tried to delete a relationship, John takes physics, but you accidentally deleted the entity itself, John. That is why we normalize. We need to separate the student from the class so that if the class disappears, the student still exists.
Okay, I'm sold. I really don't want to accidentally delete people. That feels like a massive liability. So let's start cleaning this up. The process is broken down into forms. It's almost like levels in a video game, right?
Okay.
You have to beat level 1 to get to level 2.
That's right. It is a strict hierarchy. You can't skip steps. You have to satisfy the rules of first normal form before you can even think about second normal form.
So let's look at first normal form, or 1NF. The headline concept here from the sources is atomic values.
Atomic. Indivisible. The golden rule of 1NF is one cell, one value.
The source material had a really great example of a bad table here. We have a student, let's call him Mike. And under the column courses, it just says math, physics, chemistry, all in one single box, separated by commas.
Right. And to a human using Excel, that looks really efficient. It fits on the page. It's perfectly readable. But to a database, that is an absolute disaster. Math, physics, chemistry is just one long string of text. The database doesn't know those are 3 separate topics. It just sees a sentence.
So if I want to ask the database, hey, show me everyone taking physics, it can't easily do it.
No, it has to scan every single cell as text, looking for the word physics buried somewhere inside. It's slow, it's error-prone, and it's basically impossible to sort or index efficiently. It's like throwing all your clothes into a suitcase without folding them. Sure, they fit, but good luck finding your left sock without dumping the whole thing out on the bed.
So 1NF is about unpacking the suitcase. How do we fix Mike?
We break that one row into 3 separate rows. Row 1, Mike Math. Row 2, Mike Physics. Row 3, Mike Chemistry.
But wait, now we have Mike listed 3 times. Aren't we just creating that exact redundancy we just complained about with the update anomaly?
We are, and that's a really keen observation. We are solving the nesting problem, the lists inside cells, but we are momentarily creating a duplication problem. But that's okay for now. 1NF just cares that the data is atomic. No lists, no repeating groups.
Okay, so the checklist for 1NF. Every row is unique, and no cell contains a list of things.
Correct. Once you have that, you are officially in the game. But as you noted, we now have Mike's name repeated 3 times, which leads us directly into second normal form, or 2NF.
Okay, 2NF. What is the villain here? What are we trying to kill?
The villain is partial dependency. And to understand this, we have to talk about keys.
Primary keys. This is the unique ID for the row.
Right. But in our new table, where Mike has 3 rows, what's the key? It can't be just student ID because Mike appears 3 times. And it can't be just course ID because 10 different people might take math.
So it has to be the combination of them. Student ID plus course ID.
Bingo. A composite primary key. The 2 together make a completely unique identifier for that specific row. Now, look at the other columns in that table. Let's say we have student name and course name.
Okay.
The rule of 2NF is every non-key column must depend on the entire primary key.
The whole key.
The whole key. Ask yourself, does Mike's name depend on the fact that he is taking math?
No. Mike is Mike. It doesn't matter what class he's sitting in. His name depends only on his student ID.
Exactly. It depends on only a part of the key. That is a partial dependency. And that is exactly why we have redundancy. We are writing Mike every single time he takes a class, simply because his name is glued to his ID in this specific table.
And I assume course name has the exact same issue. Math 101 depends on the course ID, not on Mike.
Correct. So we have a table trying to do way too many things at once. It's storing student info, course info, and enrollment info all at the same time. 2NF says, split them up.
So this is where we get the 3 classic tables.
Yes. Table 1 is students, just ID and name. Mike is in there exactly once. Table 2 is courses, ID and name. Math is in there exactly once.
And how do we link them back together?
Table 3 is enrollments. This table contains only the keys, student ID and course ID.
That is the aha moment for me. Because now, if Mike changes his name to Michael, I update it in exactly one place, the students table. I don't have to touch the enrollments table at all.
You have officially eliminated the update anomaly. The enrollments table just points to ID numbers. It doesn't care about the text. That is the beauty of second normal form.
So 2NF is just about removing data that only applies to part of a composite key. If it doesn't relate to the whole combination, move it to its own table.
You've got it. You are decoupling the entities.
Okay, we're feeling good. No lists, no partial dependencies. But the experts say we aren't done yet. Enter third normal form, 3NF.
The chain reaction.
The technical term in the source here is transitive dependency, which sounds like high school algebra.
It's actually simpler than it sounds. Think of it like a game of telephone. A tells B and B tells C. So indirectly, A tells C.
A to B to C.
In databases, this happens when a non-key column depends on another non-key column. Let's look at a new example. Imagine a students table that has student ID, major ID, and major name.
Okay. Student ID is the primary key. That identifies the row.
Correct. Now, major ID depends on student ID. Each student has a major code assigned to them. That's totally fine. But look at major name, let's say computer science. Does computer science depend on the student?
Not really. Major name depends on the major ID. If the ID is 500, the name is computer science. Doesn't matter which student is taking it.
Exactly. The name of the major is strictly tied to the ID of the major, but major ID is tied to the student. So the name is piggybacking on the student ID through the major ID.
That's the transitive link. It's a friend of a friend situation. Major name doesn't really belong in the student's table. It's just crashing the party because it knows the major ID.
That is transitive dependency. And the problem, again, is redundancy. If you have 1,000 computer science students, you are storing the words computer science 1,000 times in the student table.
And if the department decides to change its name to computing systems, you have to update 1,000 rows.
Exactly. And if you miss one, you have dirty data again. So the fix is the exact same as before. Break the chain. Move major ID and major name into their own brand new table called majors.
And in the students table, we just keep the major ID.
Right. So the students table just says student 1 is in major 500. If you want to know what major 500 is, you look it up in the majors table.
So 3NF is essentially every column must depend on the key, the whole key, and nothing but the key.
That is the mantra. And honestly, for 99% of business applications, this is the sweet spot. 3NF is usually where people stop. It's clean, it's efficient, and it doesn't chop the data up too much.
But there's always but in these deep dives, sometimes 3NF isn't enough.
Yeah.
There are edge cases.
There are. Which brings us to the stricter levels, the Boyce-Codd normal form, or BCNF.
I always picture BCNF as the professor who gives you an A- instead of an A because your margins were the wrong size. It's technically correct, but very strict.
It is strict. BCNF addresses a very specific loophole that 3NF misses. It usually happens when you have multiple overlapping keys.
Walk us through the scenario.
Okay, picture a table with 3 columns: professor, course, and room.
Professor, course, room. Got it.
Here are the rules for this imaginary college. 1, a professor can only be in one room at a time, so professor determines room. 2, a course can be taught by different professors, but let's simplify and say, in this table, the course implies the professor.
Okay, if I sign up for advanced basket weaving, I know Professor Smith teaches it.
Right. And if I know it's Professor Smith, I know he is in room 101.
So course determines professor, and professor determines room. It feels like a chain again.
It does. Now, in this table, let's say course is the primary key. The issue is professor. The professor determines the room. But is professor a key?
No, professor's just a column. The course is the key.
That is the violation right there. BCNF says every determinant must be a candidate key. If a column is going to dictate the value of another column, like professor dictating room, it must be unique enough to be a key itself.
It feels like a very subtle version of the transitive dependency we just talked about.
It's very similar. But in 3NF, we look for dependencies on non-key attributes. Here, the dependency involves the key structure itself. It gets academic very quickly, but the real-world problem is this. If Professor Smith moves rooms, you have to update every single course he teaches.
So the fix is tangible. We admit that professor determines room is a completely separate concept.
Yes. You split it. Create a professor rooms table with professor and room, and a course assignments table with course and professor. Now, in the professor rooms table, the professor is the key, so the rule is satisfied.
Okay, so BCNF handles those weird edge cases where hidden dependencies exist inside your keys?
Exactly. Now, if you've survived BCNF, there is one more major boss fight: 4th normal form, or 4NF.
This one's actually my favorite because the result of ignoring it is so visually chaotic. This is the explosion.
The redundancy explosion. 4NF deals with multi-valued dependencies.
Which is really just a fancy way of saying unrelated lists of stuff.
Precisely. Let's go back to our student, John. Let's say we want to track his hobbies and the languages he speaks.
Okay, John plays chess and guitar, and John speaks English and Spanish.
Crucial point here, His ability to play chess has absolutely nothing to do with his ability to speak Spanish. They are completely independent facts.
Right, knowing how to checkmate doesn't help you conjugate Spanish verbs.
Exactly. But try to put that in a single table. You have columns for student, hobby, and language. What does the first row look like?
I guess John, chess, English.
Okay. Now where do you put Spanish? You need a new row. John, chess, Spanish.
Okay, but I still need to list guitar.
So you add John, guitar, English, and John, guitar, Spanish.
Wait, so we have 4 rows, just
Okay.
to say he does 2 things and speaks 2 languages.
Yes. This is called a Cartesian product. Every hobby has to be paired with every language, even though they aren't related at all. Now imagine John learns French.
Oh no, now I have to add chess French and guitar French.
You added one single fact, but you had to add multiple rows to the database. This is the explosion. If you had 5 hobbies and 5 languages, you'd have 25 rows for one person. It's
Yeah.
completely unmanageable.
So 4NF basically just says, stop mixing unrelated lists.
Correct. If you have independent, multi-valued dependencies, they must be in separate tables.
So the fix is simple.
Very simple. A student hobbies table, which is just John chess, John guitar, and a student languages table, John English, John Spanish.
That's 4 rows total. And if he learns French, we just add 1 single row to the languages table.
Exactly. No explosion. The data stays isolated and clean.
We have covered a huge amount of ground here today. From comma-separated chaos in 1NF, all the way to Cartesian explosions in 4NF. I want to do a lightning round recap for the listener who is trying to file this away in their brain right now. I'll say the form, you tell me the villain it defeats.
Let's do it.
First, normal form.
The villain is the list. 1NF kills repeating groups and ensures atomicity. One cell, one value.
Second, normal form.
The villain is partial dependency. It ensures non-key data depends on the whole key, not just a part of it.
Third, normal form.
The villain is transitive dependency. No friends of friends. Non-key data shouldn't rely on other non-key data.
BCNF.
The villain is the weak determinant. If you determine data, you must be a key.
And fourth, normal form.
The villain is the Cartesian product. It separates independent, multi-valued facts to stop the redundancy explosion.
That is a very solid cheat sheet. Now, before we wrap up, our source included a teaching tip section with 3 practical questions. If you are building a database today, what should you be asking yourself?
These 3 questions cut through all the jargon. You really don't need to memorize the textbook definitions if you just remember these questions. Question 1. Is anything stored twice? If you are typing computer science over and over, you need a new table.
Makes sense.
Question 2. Does any column depend on something other than the key? If you know the room just by looking at the professor, but the professor isn't the key, you have a problem.
Right.
And question 3. Can I break this table into smaller logical concepts? If you are mixing hobbies and languages, split them up.
It's really just about separating concerns.
It is. It's about letting data live where it belongs.
Now, I have to ask.
Yeah.
I saw a footnote in the research about a 5th normal form. Please tell me we don't need to worry about that today.
You can breathe easy. 5NF exists, and it deals with joined dependencies, but it is extremely academic. In the real world, if you are hitting 4NF, you are already in the top 1% of database design. 5NF is rarely seen outside of theoretical puzzles. You are officially well-informed enough for the real world.
Thank goodness. I think my brain has reached its own storage limit. But looking at all these rules for keeping data perfectly isolated and structured, it leaves me with one final thought. If normalization is the absolute gold standard for accuracy,
Which it is.
then what happens when we intentionally break these rules for speed? Because there's a whole world of NoSQL and document databases out there now where people are deliberately denormalizing their data just so queries run faster at massive scale.
That is the eternal trade-off. Accuracy versus speed.
Exactly. So for everyone listening, that's something to mull over. When is the right time to build the perfect BCNF skyscraper? And when do you just need a really fast shack? I'm going to go home and try to organize my closet into BCNF.
Just make sure your socks don't have a transitive dependency on your sandals. That's a bad look.
I'll do my best. Thanks for listening to The Deep Dive, everyone. Go forth and normalize.
See you next time.